Let us begin our study of physics by looking at all the forces, right? So we'll touch upon all these forces, and we will not go into detail of any of these right now. Some of these you might already know, but the key idea here is that all the interactions, everything that you see in this universe is due to these four forces. Okay, your pushes, pulls, friction, viscosity, the movement of sun, the planets, everything can be condensed to these four forces, and we will try to understand why that is the case using some examples. But before we do that, let us understand each of these forces in turn and what it actually what does it entail, what does that force control, how does it behave. So the first one is gravitational force. We already know that universal law of gravitation is given by the famous formula, right? So the force of gravitation, Fg, is equal to G, which is the universal constant of gravitation, m1 m2 upon r square. So what does it mean, right? What does these symbols, what do they mean? Let's just delve into this a little bit. You might already know this. See, this is G is just a constant of proportionality. It is just a constant, so not of much importance here. We'll just ignore it. It does not tell us about the behavior of the force as much. The force of gravitation, it boils down to, it is proportional to the product of the masses. So as the masses, as they increase, the product would increase, and the force of gravitation between those two masses would also increase. And the force of gravitational falls off as the square of the distance between the two objects whose interaction we are studying. So as the distance increases, the force of gravitation does not fall off linearly. It does not if the distance becomes half, the force of gravitation does not really become half. It becomes 1/4, right? And that is the key here. This is known as inverse square law, right? This is not inverse law. It is inverse square law. Square means that the force of gravitational would fall off proportional to the square of the distance. That is what it means. And this is very important because the same inverse square law would also come in another force, and we will study that in 2 minutes. See, we know that it does not require any medium to propagate. Gravitational force just propagates from one place to another without any medium. It travels in vacuum, if you want to say it so. And this is important specifically for gravitational force because previously, in very, very early days, people used to think that there was a medium when none existed. When there was vacuum, there was a medium, and they called it ether. And they thought that this ether was actually responsible for transmission of forces. But that is not the case. We now understand that the gravitational force can just go over large distances without any medium. Another important thing about the gravitational force is that it is always attractive. The two masses, if they are there, it would always cause attraction between them. And if you think about it, these two masses are there. The masses are so small, but there is gravitational attraction between these two as well. In the same way as there is gravitational attraction between the sun and the moon, between the sun and the earth, between the earth and the moon, right? The same law of gravitational applies here on earth when the apple falls to the ground, and the same law of gravitational applies on in the case of celestial bodies. And that is why it is so important. The Newton's discovery was so important because he created something which applied universally. So this is about the law of gravitation. The next important law, which some of you might have heard, is the electromagnetic force. Now, electromagnetic force has two components. One is the electric part of it, and the second is the magnetic part of it. So when do they come into play? They come into play when the charges are static. Then there is only electrical interaction between them. Then there is only electric field. When the charges are in motion, then we have magnetic field as well. Then they create magnetic field, and then we come to the magnetic interaction. So for now, we will be focusing on the electric aspect of it, and we'll assume that the two charges are just static. And in that case, the electric force Fe between these two charges, the electrostatic force between these two charges, is given as Fe is equal to K and then Q1 into Q2, where Q1 is the charge on these particles. Q1 and Q2 are the respective charges, upon R square. Notice the similarity between the gravitational force and the electromagnetic force. And these are the two forces which we encounter in our normal life. In our normal life, when we are living, we only encounter these two forces. The other two forces that we will study are nuclear forces, are only present when the distances between two particles is very, very small, subnuclear or nuclear, right? Which means that they are only present within the atom, more or less. So again, here Q1 and Q2 are the charges of two particles, and like we said that in the denominator there is R square, right? So like we said before, this is also an inverse square law. It also works over large distances. Okay, so actually it is present for infinite distances, but it only falls off as the square of the distance. Again, it does not require any medium to propagate. Now the difference between the electromagnetic and the gravitational force is that mass has only one kind. There is just one thing, mass. Okay, there is nothing like a negative mass. You can only have a mass. So which means that the gravitational was only attractive. But charges come in two flavors. They can either be positive or they can be negative. When the two charges are the same, that means positive positive or negative negative, in that case the electrostatic force between them is repulsive. The Coulomb's force is repulsive between the like charges. Between the unlike charges, that means positive negative, like proton and electron, between unlike charges, this force is actually attractive. So that's what holds the protons to the nucleus. Now another thing to understand here is that the next question which should automatically come is that, sir, if the electrons are attracted to the nucleus and that's what keeps the electrons in the atom close to the nucleus, the protons are there in the nucleus. So there is a problem because all the protons are positively charged. So they should just fly apart. How can we keep them together? And that we will study in just a second. Okay. There are other kinds of forces which are present at the nuclear scales, and we will study that in the next slide, in the very next slide. So we already saw that these are present between any two bodies which have charge. Now this electromagnetic force is very, very important. See, the gravitational force, it is present between any two bodies. That is very obvious when it will be present and when it will be not present. So any force you can, for example, if I ask you whether the force of friction is a gravitational force or electromagnetic force, you can simply say that it cannot be gravitational force, because the gravitational force cannot be so strong between these two bodies. Okay, so the gravitational force is actually very, very weak force. We need massive objects to produce any kind of a meaningful interaction. So for example, the mass of sun, the mass of earth, mass of moon are very, very large. To produce that kind of significant interaction, we would need very large amount of mass to produce significant gravitational attraction. In case of electromagnetic force, that is not the case. Even small charges which we encounter on our everyday scale, for example, the charge of the protons, the charge of the electrons, can produce meaningful electromagnetic force, and that is the key. The gravitational force between two protons is negligible. It is not sufficient. But between two protons, the electromagnetic attraction is actually very large. It is very, very large. It is almost 1,000 times large, the electromagnetic force. So most of the interactions that we see in our daily life cannot be due to the gravitational force. Okay, in normal terrestrial objects, most of these interactions, for example, viscosity, friction, these interactions are because the chemical reactions that we see. These interactions are the underlying, all of these interaction is the electromagnetic force, and that is something that we need to really keep in mind, because sometimes you might be asked a question that what is the underlying force, what is the basic force responsible for friction, and the answer should come out to be electromagnetic force. And we'll just see that with an example, right? See here, think about it. Why does electromagnetic interaction produce friction? If you think about it, here I have a matchstick and a match. These are very simple objects. There are atoms sticking out right here, right? So this surface, although it might seem a little smooth to you, but if you look at molecular scale, if you go very, very minutely, if you look at it, there are small undulations on this surface. Similarly, on this surface also, this is rough, right? So there are small undulations here also. So what happens when I rub this matchstick on the surface of the matchbox? What happens then? The individual atoms are actually torn apart. And what is keeping those individual atoms together? if you think about it, the underlying forces of attraction between two atoms, between two molecules, is electromagnetic attraction. So that is what keeps the atoms to attach to other atoms. So those are that is the force responsible for bonding between the atoms, between molecules, right? And those when I'm using this friction, when I am rubbing this matchstick against the matchbox, I am tearing those bonds. I am just ripping those atoms apart. And of course, for that I have to spend energy. And where does that energy go? That energy comes out in the form of heat. And like this matchstick, as we'll see just now, right? So this is the simple example of how I was able to produce friction because of the electromagnetic attraction which existed in the between the electromagnetic attraction which existed between the atoms right here, right? And when I'm tearing those atoms apart, I am then actually using energy, and that energy is lost to friction. That is what we call the force of friction. Okay, so friction is entirely electromagnetic force. It is electromagnetic force is responsible for that friction. Same thing happens with viscosity. When I am moving in fluids, like for example water, we know that there is van der Waals attraction between the molecules of water. When I am tearing through water, then I am breaking those bonds, and to break those bonds I am using energy, and I am encountering some resistance, right? And that resistance is actually the force of viscosity. I am naming it viscosity, but it is not a separate force. The underlying force is electromagnetic force only. And similarly, all the reactions, all the atomic bonding, everything that we see is due to this electromagnetic force, and this is the most important force in our everyday interactions, everyday observations that we see. Now, next we move on to two other forces which we will never encounter in our daily life. Okay, but before we do that, let's just compare the gravitational and electromagnetic forces. Like I said, gravitational is very weak, electromagnetic forces are very strong. If you apply the same to the similar objects, for example, if I apply the gravitational force, if I compare the gravitational force between two protons and electromagnetic force between two protons, the gravitational force is very weak. It is almost 1,000 times less. So therefore, the electromagnetic force dominates in all our interactions, right? So this is very, very important. You have to understand this. You have to always keep this in your mind. Now the next two forces are nuclear forces. They are only present at nuclear and subnuclear scales. The first is strong nuclear force. Strong nuclear force is not an inverse square force. This kind of force, the strong nuclear force, falls down very, very quickly with distance. Okay, so it is not inverse square. It does not last forever. Okay, it does not go to the infinite distances. It again does not require any medium. That is the thing, and it can either be repulsive or it can be attractive. It can be both. See, the particles inside the nucleus, they are protons and neutrons. The two of them are together known as nucleons. Okay, so this strong nuclear force is between two nucleons. It is present between proton-proton, it is present between neutron-neutron, and it is also present between neutron-proton. It is not that it will be only be present between two protons. No, that is not the case. It is present between all the particles inside the nucleus. For distance of about 1 femtometer, which means that 10 to the power minus 15 meters, this is very, very attractive. So it is strong, very, very strong, much more strong than our electrostatic repulsion, and that is what keeps the nucleus together, right? The strong nuclear force, it is strong, that's why it's called strong. It is very, very strong, and the strong nuclear force keeps the two protons together, even though electrostatic force would try to push them apart, because it is much more stronger than the electrostatic force at the distances we are talking about. So 1 femtometer, till those distances, it is strongly attractive. Beyond that, to 2.5 femtometer, it exists. After 2.5 femtometer, it is gone. It no longer exists. It ceases to function. At distances below 0.7 femtometer, okay, so now I'm going below 1 femtometer. Below 0.7 femtometer, it becomes repulsive. So it means that if I try to bring two protons or two neutrons very close together, they will not come, because this strong nuclear force, it is very strong and it becomes repulsive. And that is what keeps the nucleus from collapsing, right? In the sense that nucleus is very rigid, Right? We saw it in the Ernest Rutherford's experiment also. The nucleus is very rigid. He said that it was almost like the bullet hitting a paper. So imagine how rigid the nucleus must be. And it is rigid because this particular force, 0.7 femtometer, after 0.7 femtometer, if I try to push two nucleons beyond that, it becomes strongly repulsive, and it is very strong, right? And it is repulsive, so which means that I will not be able to push nucleus. I will not be able to make it any smaller than what it is, and that is gives the rigidity to the nucleus. And of course, in case of if you compare it only in the case of protons, right, where we'll use two objects, it is 1000 times more powerful than the repulsion between two protons. Sorry, 100 times, not 1000 times, 100 times. The next is weak nuclear force. Now, the weak nuclear force, as the name suggests, it appears in the nucleus only. It is present at subnuclear levels. It is only present at scales of 10 raised to power minus 16, which means 0.1 femtometer. It is present only at the scales of 0.1 femtometer or less, and it appears only in certain nuclear processes, such as the beta decay of nucleus. So there is a certain interaction inside the nucleus which happens, which is known as beta decay, and only in that those processes this interaction comes. It does not require any medium like the other forces. It also does not require any medium to propagate. See, beta decay, what happens in beta decay? The nucleus, it emits an electron and a neutrino. So neutrino is an uncharged particle, right? There are many particles inside the in the physics. Okay, so protons, neutrons, electrons, that we understand. Positrons is the positive sort of particle of the electron. Some of those you might have heard, but there are very many particles in the quantum mechanics, if you go into the subnuclear realm, and one of those particles is neutrino. So neutrino is an uncharged particle. Okay, and in the case of beta decay, the nucleus would emit a electron and a neutrino. Okay, so that is the process of beta decay. That is what is meant by a beta decay. See, the weak nuclear force is in between. Okay, it is not as weak as the gravitational force, but it is much weaker than the electromagnetic and strong nuclear forces, right? So it is stronger than the gravitational force, but weaker than the other forces. One of the things to understand here is that why are the forces suddenly, like, see, forces, we always said that they were like pushes and pulls, but here we are saying that forces are actually present in the case of beta decay, right? When emissions of particles are happening, then there are certain forces which come into play. Why is that? See, the thing about force is that we understand forces the way we understand them, like gravitational force, like electromagnetic force. We understand them as something which is transmitted over distance spontaneously, which is just transmitted. Okay, but that is not how quantum mechanics treats forces. In quantum mechanics, if you think about it, then the mass is mass. You understand that mass, if there is mass, there has to be certain things present to create that mass. For example, if there is mass, there has to be neutrons, there has to be protons, there has to be electrons, and only when these things are present, you will get mass. So mass is because of particles, we understand that. In quantum mechanics, all the forces are also transmitted due to particles. So this is the most important thing. Okay, in quantum mechanics, there are particles known as bosons, which are responsible for transmission of forces. So behind each of these forces, there is a boson which is responsible for transmission of that force. And in this weak interaction, I am saying again and again, okay, I am not using the word nuclear force. In this weak interaction, when it happens inside the nucleus, certain bosons are exchanged, and those bosons correspond to the weak nuclear force. Okay, so that is how we understand the relation of the weak nuclear force to the particles. Okay, now with this, we create a summary of all the forces. If we compare them all together, it is given in this table. Gravitational force, we know, is very weak. Okay, so think about these forces appearing only on two protons. Okay, so if these forces, if we compare the gravitational force between two protons to the electromagnetic force between two protons, weak nuclear force between two protons, right? So we are comparing it to the same kind of particles. If we compare it that way, then the gravitational force turns out to be very small, and strong nuclear force turns out to be gravitational force turns out to be very weak, extremely weak, and strong nuclear force turns out to be very strong. Right? Range is given, and then on which particles these forces actually act, right? So for electromagnetic force, of course, you need charges. It does not happen between any two particles. You need charges for electromagnetic force to happen. Similarly, for gravitational force to happen, you need masses. If a particle is massless, there is no gravitational force on it. Okay, that is the most important thing. So gravitational force does not happen on all objects in nature, right? So here it is written all objects, and that is incorrect. Okay, it does not happen on all objects in nature. It happens on all objects in the universe which have mass. If a particle is massless, there is no gravitational force on that, and we will see particles which are massless. Okay, so this is the summary of all the forces. Now, like we said, one of the most important objectives of physics is to unify our entire understanding of this universe into as few laws as possible. Okay, and here are some of the scientists who have done great endeavors in unifying the various things that we see, right? Two observations might seem completely different. For example, apple falling from the tree and the moon rotating or the earth rotating around the sun. These two observations might seem completely different, but Isaac Newton was the scientist who actually said that they are due to the same law of gravitational applies to both the domains. Similarly, right, so this is the first one. Similarly, the Ørsted and Faraday, they actually said that electric and magnetic phenomena are not two different things. They are the aspects, they are the two sides of the same coin. When the charges move, it creates magnetic fields and essentially giving rise to the unified domain of electromagnetism. Maxwell was the one who actually unified electricity, magnetism and optics. So electromagnetism we know, and Maxwell showed that optics, the light itself is an electromagnetic wave. How does the light propagate? How does the light go from, for example, that light bulb to me? How is it coming? It is coming in the form of electric and magnetic waves. So Maxwell actually showed that in his 4 equations. That was one of the big unifications. Now we have seen the two forces, the weak nuclear force and the electromagnetic force. We have seen those two forces. Glashow, Salam and Weinberg, right? We already saw it in the contribution of Salam. But these 3 scientists together said that the weak nuclear force and electromagnetic force can be unified when the temperatures are very, very high. Such were the temperatures in the time of Big Bang. So in the time of Big Bang, the weak nuclear interaction, the weak nuclear force and the electromagnetic force were actually unified. They were one and the same thing. See, those conditions are not reproducible now, but it gives us confidence, right? When such studies happen, it gives us confidence that if those two forces, which are so different from each other, are actually the same, the other forces must have the same underlying fabric, right? It gives us that confidence. Similarly, the work of Rubia and Mir, they were able to verify that experimentally that the weak nuclear force and electromagnetic force are actually not two different forces, but under certain conditions, in very, very high temperatures, they become just one. Einstein, one of his great goals was to create unified field theory, and he died doing that. And his goal was to actually unify the electromagnetic force and the gravitational force. And that was his ultimate objective. And you can actually see why he was doing that. Because the two forces are so similar. The only difference is in one case we have mass and in one case we have charge. And Einstein had already shown that E is equal to mc square. So he had some insight that okay, the mass can be converted into energy. Okay, so if with all of these things being related together, I can envision, right? And you can also see that why Einstein was thinking that these two forces, electromagnetism and the gravitation, they can be brought together into a single force. Right? I always say that our work, our understanding of these fields is built on the shoulders of these giants. Okay, and this might seem very useless to you. This might not come in the exam. That is not the case here. But when we learn about these people, when we learn about what they have done and how much trouble they went through to come to these conclusions and how we are using their conclusions now in our everyday life, how it has changed us, we can sort of appreciate, we can develop an interest in the subject, and that interest takes us a long way. See, physics is much more than solving a few questions. Any science, any subject is much more than solving a few questions. And that is what the entire goal of this first chapter is, to develop your interest in this subject, and hopefully we have been able to do that. Thank you.